start up. So I want to point out, I did have a typo up here last time, even though we didn't discuss this. I had V sitting right there, and the variance of V can involve V. Variances and expectations always involve the hyperparameters, whatever it's conditional on. So change those to omegas. Let me tell you a little bit about what the Wishart distribution is. So this is a distribution over positive definite matrices. So V is symmetric and positive definite. So you can do things like invert it. So you can do all the stuff you want. So where we usually use this is for covariance matrices. So covariance matrices are supposed to be positive definite. So if they're going to be useful to each other. There's something called positive semi-definiteness, and that's when the likelihood function will have a ridge in it. So if you have multi-collinearity or something and you compute a covariance matrix, or if it's rank deficient, something like that, then it's not going to be positive definite. But a definition of this would be the Cholesky factor exists. That's one thing. So that means R transpose R, which is equal to V, exists. Or you might say the eigenvalues are positive. And what you're really thinking about is if you take a normal distribution and you have a positive definite matrix in there, the likelihood function will look like a paraboloid. So in any margin, it looks like a parabola. And if you ended up making something, if you had something in there that was positive, or if it wasn't positive definite, so it wasn't negative definite and it wasn't positive definite, see inflections in that shape. And it wouldn't be this unimodal sort of thing. And so if you had negative definiteness in there, i.e. a zero eigenvalue, it'd build a flat ridge in there. You wouldn't be able to identify the peak of the distribution. So lots of things you can think about when you think about positive definiteness. Let me tell you what some of these other things are. Omega is also symmetric and positive definite. And it has something to do with the expectation of everything. So in some sense, in some way, omega is determining where these matrices are centered. Now it's not quite exactly that. It's you also have this scaling parameter right here. The scaling parameter is a scalar. So gamma is a scalar. And it needs to be chosen so that this thing is positive right here. So gamma needs to be greater than k minus 1. So that's a restriction on the space. Very typically, what I'll do if I'm using this as a prior on covariance matrices, which we'll examine in a minute, is what I'll often do, so very often, I use PV using the same notation as before, and I'll take my matrix right here and I'll scale it by gamma. And the reason I'll do that is so that the expectation for V is equal to omega, so that it's that thing. So when I take omega divided by gamma and I multiply it by gamma, then I can understand where everything is centered. Now I'm not going to do that for all of these examples, but when I use these in practice, I always parameterize like this. Changes the variability a little bit. We need to be a little bit careful when we play around with this equation. But basically, when we parameterize it like this, we're centering everything around some matrix, some positive definite matrix, and the distribution is just the distribution of matrices around that matrix. I think that's pretty easy to think about. This is just a note. show is that this is the conjugate prior for the inverse of the covariance matrix. So let me just remind you of the problem that we're looking at, the rat weight problem. So recall, from Gelfand and Smith, and there's some other people in here, and I'll point out that when most people refer to the Gelfand and Smith paper, they're talking about the JASA paper. And so that comes out just a little bit later. And so they wrote a couple papers with the scientists employing this Gibbs sampler, and then they wrote it up real nicely for JASA, which is a high-level stats journal. It's a flagship journal. So does anybody know what that stands for? It's not that hard, huh? If you know what the ASA is. So yeah, that's kind of the American premium stat publication. And it would be the equivalent of something like the Journal of the Royal Statistical Society Series B or Series C, depending on if it's applications and case studies or theory and methodology. So JRSS is partitioned into two separate journals, and JASA is one journal, and there's a T&M side of it, and there's an A&C side, applications and case studies, theories and methods. And the notable Gelfand and Smith paper that's much more mathematical than the one that you guys are looking at, that's in theory and methods. So it's probably one of the most cited papers out there. So I think nowadays people don't cite Gibbs sampling quite as much, that it's become rather ubiquitous for Bayesians. But that's the paper that you would typically cite. So you wouldn't cite necessarily the paper I posted, and if you search on this, you'll see like 3 different RAP papers, and then you'll see the full-blown thing. That's a good way to sculpt your career, is go work with people, get some applications, write some studies, get about the idea, and then go to a high-level theoretical journal, and then publish everything you really wanted to say. So I like that one. So I just think if you're going to come up with good theory, it should be embedded in some good application or real problem, or else you're going to be solving some problem that doesn't really exist. Now, if you're a mathematician, that's okay. So you're allowed to do that. 100 years later, somebody will figure out the application. Okay, so the paper looks like this. So this is going to be the weight of the rat at time t. And we can let I go from 1 to n and t go from 1 to cap t. You can come up with your own notation in your homework if you'd like for that. So this just looks like this. Alpha I plus beta I times t plus some errors. And the errors are going to be IID errors that are normally distributed with 0 mean, so that is the mean function, invariance sigma squared, and I usually like to write that down as the precision. You'll note that in the paper, they end up working with inverse gamma distributions for all of their precisions. So that's a good exercise that I'm going to ask you in the next homework to evaluate whether or not you like their priors. So what you're going to be doing is just changing the hyperparameters in those priors that you use for your pseudocode in this homework, and you'll just change those inputs. But you'll probably have to do a transformation so that you have the exact same distributions. And I'll let you work through that. I mean, you can discuss whether or not you like their priors. Eric?
Does that model for the error term, I noticed that it's only a t index, so is it only dependent on time?
Yeah, that's right.
Okay.
So they all have, so you could end up doing something like this and end up letting each rat have its own variability. And if the rats vary differently, you would probably want to do that. And so I'm not going to justify their model too much and say whether or not they should have done that. So, but they all share the same variance terms. I will point out if we did something like this, this would be called like a fixed effect, where this would be called a random effect, right here. And for a non-Bayesian, they would treat those things totally differently. But for a Bayesian, if you're going to play around with this, you would have a random effect on beta, and it would look and feel like a prior. And if you're going to operate as a full-blown Bayesian, you would place a prior on that. And everything would look exactly the same when you're coding up a Gibbs sampler. So fixed effects and random effects models, when you put them together, people call those mixed effects models. But to a Bayesian, you operate exactly the same on all of the parameters. There's no difference to you. The only difference is your conceptualization of what induced the randomness. So if you're placing a prior on something, you're probably thinking about properties of your posterior and what you're trying to estimate and what the properties of that estimator might be. For random effects, you're thinking about modeling dynamics. There's certain things that are random out there in nature. And you want to control for the grouping of that randomness. So classic example would be something like if you had a large swath of Stat 101 classes and you had 3 different instructors teaching them, there might be a teacher effect in everything, and you would want to control for that. And so there would be a random effect attributed to each one of the teachers, and there would be some population average as well. You would want to estimate that, and you would want to distinguish the variability in the classes depending on who was lecturing. In statistics, that is the name of the game, is to try to control your different sources of variation and model them appropriately. So if things are coming from mixtures or different distributions and you call it all one big distribution, you're going to overestimate all of its variance probably. You're going to treat its variance wrong. And so there's room for improvement there. The model is just this random effect model right here, where both of these are random parameters. So I'll just say alpha I and beta I are coming from some distribution. So the conceptualization is each rat is getting its parameters that maybe map over to its propensity to put on or take off weight, and it's coming from some distribution itself. And so we'll just call this, I'm going to change my notation maybe to beta, alpha, beta, beta. And then I've got some covariance term in there. So this covariance is a 2x2. And one of the key problems at hand in the Gelfand and Smith paper is, are those 2 parameters, alpha and beta, correlated with each other? Which would explain whether or not their initial weight coming into the study has something to do with how they put on weight or how they take off weight. And my guess is, yeah, I bet they have something to do with each other. So, anyway, so the question is how do you estimate all of these parameters? And truth be told, it's probably not all the philosophy that we talk about in class that has transformed the world into a bunch of Bayesians. But it's probably this Gibbs sampling thing, or MCMC, or trying to jointly estimate all these parameters. You've got a computational device to do it. So I will point out that my friends that play around with things like mixed effects models, usually when they're updating that parameter, they'll use MCMC to do it. And what the classicists will do, usually to deal with that parameter right there, is they'll maximize over that parameter. So they'll maximize that parameter and run MCMC there. People have gotten sick of doing that, and I've noticed a lot of classicists just saying everything's a random effect and I'm going to run MCMC. So, but I'm not going to say I'm a Bayesian. So personally, I don't care what you do as long as you do the right thing. So I don't care what you call it, just as long as you're doing things that are sensible. So that's some version of everybody getting along. Okay, any questions about the model? Okay, so let's just take an aside. Keep in mind that this thing right here, this layer of the model, this is just normally distributed. Right here, we're going to need priors on all of these different parameters. So we'll need priors. phi. I'll say we'll need them on the theta, which I'm going to call theta alpha, theta beta. So I'm just going to nickname that thing. We'll use that notation a little bit later. And so I'm going to probably call these things later on, just for notation. This is probably going to be theta I right here. So they have something to do with each other. So I'm probably going to call it all the same sort of thing. So later on we'll use that notation. I'll change from the alphas and betas. And personally, I don't like writing it out this way. The likelihood using all this, and I'm not going to expand all the matrix multiplies. I'm going to keep it in matrix form. And your computer enjoys that. So your computer can compute all that stuff in matrix form much faster than if you expand all the squares. We'll need a prior on sigma as well. And so we've already discussed this prior. I'd probably place a gamma there because it's conjugate. There's other good reasons for it. And when we get into the Jeffreys prior, we'll figure out that the Jeffreys prior is 1 over phi, which is the limit of that conjugate prior. So conjugate priors are still usually a good idea, even though they're computationally tractable and easy for us to play with, but there's good theoretical reasons to use them as well. Probably use a normal prior there. And we could adjust those hyperparameters depending on if we had subjective knowledge of the problem. And that's what they do in the paper, or you could end up using the reference prior, the limiting prior, the flat prior there. And maybe when you do your Gibbs sampler, you might want to check that and see how does everything work with just standard priors and how does it change the answer. My suspicion in their paper is it matters. And so what I usually think about scientifically, if you do two things that you think are reasonable and it makes a big difference, you should pause. So, and go have a long, lengthy discussion about what is really going on and do you have enough data to really estimate all this stuff. In the paper, they only got 5 rats going on and the number of time points is 30. So it's not much data. Okay, and so this, they're going to end up placing maybe an inverse Wishart on that, but I'll show you using the Wishart on the inverse of that parameter. So again, this is all coming from a normal form, so if you can kind of envision what the likelihood function for all of this is, you can realize that, oh, I'm going to place just the conjugate prior on this. So it's just coming from a normal. So let's look at that. So take a step back. Leave this on the board. We'll just demonstrate the conjugacy of this prior. So I don't want to do everything for you. So I'll just make the problem slightly simpler and you can butter this all up for your homework. Example. Say that I've got some multivariate responses, so I'm going to say xi's. And what these xi's look like are really just xi1, I'll say x1i, x2i, x3i to x, I'll say pi. So this is going to be p-dimensional. So this is going to be distributed normally. I'm going to say that it has some mean. I'll just write that down as mu. That's also p-dimensional. Just be entirely clear about this. There would be like mu1 down to mu p. So p-dimensional. And then you're going to have some covariance in here. And that's going to be a p by p, and that's going to be positive definite as well. and we're going to have a bunch of data. I is going to go from 1 to n. And so let's say for our illustration, mu is known and it's fixed. Now, of course, in a real application, mu is not going to be known. So what are you going to do? You're going to work out its full conditional and probably bury this whole thing into a Gibbs sampler. So let's just work on the layer for the covariance matrix. In a second, I'm going to change that to the precision matrix. So we'll say that this is known. Again, all this stuff that seems like I was just simplifying too much, this is what we typically do as Bayesians, is we work out full conditionals, which is a little bit easier of a problem, and then we bury everything into a Gibbs sampler, and the Gibbs sampler is basically auto-integrating for us. It's also exploring everything and giving us samples that estimate our distribution that we want to base all of our inferences on. Okay, so let's just write this thing down. So we're going to need all of our data. So f of x, and this is going to be my full collection of my x1 down to x, I'll say n. So I'm going to have n of these p-dimensional vectors. We could do this with just one data point if you wanted to and play that game, but let's just see what it looks like if I've got n of these things. We'll look at our posterior estimates. We'll see if they make sense. So this is going to be given mu and sigma. This thing is just going to look like, I'm going to have some 1 over 2 to the pi. I'll leave that in a second, and we can write that out in a second. So this is going to look like a product over 1 to n. So I'll write down proportionality. And I need the multivariate normal form. So why don't you guys just help me out with that a little bit? There's a part that involves sigma that's out in front. So I've got this part that involves sigma, and I probably need that part, and I can't throw it away because I'm going to be doing inference on sigma and trying to learn what it is. And then I'm going to have this e to the minus 1/2 part. We need to fill in all this stuff. What goes here? Determinant of sigma.
N minus 2.
Which one is it? Negative 1. So we've had this discussion before. Does this go inside or does it stay outside? It doesn't matter. So you could plug it inside if you wanted to. A lot of textbooks have this. These are exactly the same things. So if you compute the minus 1/2 power of a matrix and you take a determinant, or you take a determinant of that matrix and you take the minus 1/2 power, it's not a coincidence that those numbers are exactly the same. So it doesn't matter which way you do it. Okay, what goes here?
X minus mu, xi minus mu,
xi minus mu
transpose,
transpose
sigma inverse xi minus mu.
sigma inverse xi minus mu. You can at least know what the normal distribution is. So good job, we've got it. What goes over here? What's the normalizing constant that we don't really care? Does anybody know what it is? 1 over 2 pi square root.
Yeah.
To the nth power. Yeah. Is there anything to do with p in there?
Yeah, it's raised to p.
Which one?
It's okay. 2 pi raised to minus
P times n over 2.
Then there wouldn't be a square root.
Then no square root, right? Yeah, I got it twice. Yeah, exactly.
Yeah.
We can get this right together. This sort of stuff that we do when we code something up and we're like, what's wrong? Okay, easy to fix on the chalkboard. So the p goes out there. So, and then we producted up to p. N times, I really don't care if you know. So if I do ask you to write out a distribution completely and state the distribution, and I ask you to write out what the density function is, then I'm asking for it entirely. So If you did forget to put this, it would be like a minus half or something like that. If you missed that, that might tank your whole problem. Okay, so that's our sampling distribution. So the key to recognizing likelihood functions is to write down their sampling distribution, recognize what's a constant and you can throw away, and recognize what's the kernel of that distribution. So if we were doing inference on mu, all I'd need is this part. So still wouldn't need that, but since we're going to do inference on sigma, we definitely need that. So I usually like to write out the whole sampling distribution when I do all of this. Okay, let's just look at this. So this is going to be some matrix to some power right over there. We've got something just like that. It's a little bit different that the power is sitting outside of the determinant, but that's not hard to fix. We just pull that thing right outside. And now it looks the same. So, and then we have e to the minus 1/2 trace of everything. And that does look a little bit different than what we have right here. I want to point out this thing is a scalar, and this thing also is a scalar once we take the trace, but there's matrices sitting up here. And so we need to recognize this thing is the same thing and it doesn't quite look the same. And so let's try to write it out correctly. So I'm just going to take this part. We'll redo this. This is going to be sigma absolute value e to the minus n over 2. So I pulled that outside of the product. And I'll just chisel away at this thing inside of the product. I goes from 1 to n, e to the minus 1/2, and here's my step. I just write trace. xi minus mu, transpose sigma inverse, xi minus mu. So I just buried it in there. How come I can do that? It's a scalar. So trace of the scalar is that same scalar. So I haven't changed anything because that's a scalar. So if there were a matrix in there, you can't just do that. Okay, so let me just do one more thing. I'm going to take this and pull that over to the other side so that I've got this thing isolated over on the right-hand side. So I want to point out that our random variable is right there. I also do want to point out the typical notation has omega right here, and it has omega 1/2, or omega to the minus 1 right there. This is a common mistake that I always make where I forget about that. And then there's a missing inverse sign somewhere. So if I do make that mistake in the end, you will correct me on it. Okay, so as you guys might know, trace of A, B, C is equal to the trace of CAB is equal to the trace of BCA. So you can do all the cyclic permutations. So I pulled that C and I put it right here. That's that. And then I took the B and I plugged it over on the other side. That's a homework problem for you to prove that that's true. So I can cyclically permute everything inside of a trace, and it's still the same quantity. Everybody good with that? If you're not, you will enjoy that over the weekend and prove that. All you have to do is just pull out your linear algebra to prove that. Or you can work out and just do it by scratch. How you would do it is you might just work with a 2x2, show that it's true, and then do induction, something like that. You might have a cleaner proof that you can present as well. I usually don't love looking at induction proofs if you don't have to, and you don't have to do it that way. You can do it directly. This is in every linear algebra book. So I can change this real quickly and rewrite that is e to the minus 1/2 trace. This is going to be xi minus mu times xi minus mu transpose sigma inverse. And now this is starting to look pretty good. That's a matrix right here. So this is an outer product. not an inner product. So inner products are going to be these scalar things, and the outer product is going to be a matrix. And so this might make you feel pretty good, because if you were going to estimate the covariance function, usually you use the outer product forms to do that. Okay, so let's just rewrite all this stuff. So what we have so far is f of x given mu and sigma is going to be equal to, or proportional to, if you'd like, sigma to the minus n over 2 times e to the minus, and I'm going to pull my sum inside of everything. So I'm going to take this product and pull it into the sum. Be careful when you do this. I'm going to have two different sigmas floating around, and they mean entirely different things. So I'll be really clear about my indexing. I goes from 1 to n, right there. So that's an operator and not the parameter. And then I'm just going to have the minus 1/2. I just pull that out in front, and then I'll have all this stuff that we wrote down before. So trace of the outer product, xi minus mu, times xi minus mu transpose, times sigma inverse. And that's starting to look pretty good. Of course, there's this summation sign that's floating around, and I can tuck that summation into the trace. So we're going to use this other property, trace of A plus B is equal to the trace of A plus the trace of B. And I can see the zeal on my face as an undergraduate going, I believe you. You know, no proof required. So one way to think about the trace is the sum of the eigenvalues. But maybe an easier way to think about a trace is the sum of the diagonal. And if you think about it that way, this proof is a one-liner, and that's also what we're doing. So we're going to use that property and just tuck this sum inside there, and we can pull it in and out of the trace. So we'll do that. So this is going to be equal to sigma to the, and I'm going to just change something real quickly, and I'm going to take that minus sign, and I'm going to bury it back in here so that we can recognize this common parameter, sigma inverse, that we're talking about. So we have a sigma in one part, and we have a sigma inverse in the other part. Easy to fix. Minus 1, and that's to the n over 2. So I can just pull those producted things back and forth. So e to the minus 1/2, this will be trace, sigma sum of my xi's minus mu, xi minus mu transpose times sigma inverse. And I can think about this as its own thing right here. And once we get to that step, you recognize that looks almost exactly like this thing right here. So you can see what that is. You can see what that part is. And it doesn't take much imagination to figure out if I multiply something that looks like this, of course, parameterized in terms of sigma inverse, into something like that, it will preserve its form, i.e. its conjugate. So let's just do that. So the conjugate prior for sigma inverse. And again, this is my preferred parameterization that I work with. And in large scale computations where you're looking at huge covariance matrices, they could be dense, but the inverse might have zeros in there. It might be sparse, depending on the process. So if you're curious more about that, you can read through that PDF that I put up on the web page, and that'll tell you what the zero entries mean in a precision matrix. So you can reduce a lot of things. Also, those zeros allow you to factorize the normal distribution. So you can factorize it very nicely. And it gives you an opportunity for updating just the little blocks that are non-zeros in the precision update. So it gives you a way to factorize that big matrix. We're not going to walk through all of that, but sometimes when people are playing around with this, they'll talk about doing hyper-inverse Wishart sampling, and what they really mean in the hyper thing is there's just a whole bunch of these little sub-matrices that they're updating one at a time. And those sub-matrices represent groups that are conditionally dependent on each other. So the typical language that we use in statistics is those are cliques. And that's exactly the same word that we learned in high school. So there's different groups that hang out together. So that's in high dimensional land, that's still current research that people employ all the time. And trying to do that very fast is the name of the game. So 15 years ago, it was really current research. Everybody was on that problem of how to do that fast, how to represent everything very quickly. And you could come up with graphical illustrations of what those clique formations look like. And so sometimes you'll hear people call this graphical Gaussian modeling. And so there is no graph, it is just the same normal thing with different clique structures, and you could draw the conditional dependencies as a graph, if you would like. That's a popular thing to do. Personally, the graphs never helped me. So, but everybody has their way of thinking about problems. And it sounds cool. So that's score 1 for a statistician, finally coming up with something that sounds cool and not waiting for a computer scientist to do it for us. Okay, so let's just see the conjugate prior for sigma inverse is Wishart. And we'll use the same parameterization. I'll say this is gamma and omega. So there's still just 2 parameters in there. I use the same notation for that. Again, when I do this, I usually scale everything by gamma right here. I'm careful in all my updating so that I can interpret where I've centered the prior. Okay. So let's just show that. So here's my likelihood function, essentially. So we've written down everything up to proportionality, and I'm going to wave my magic wand, where I no longer think about this as a function of the data, but I think of this as I plug the data in, and I think about it as a likelihood function over sigma. So our likelihood function on sigma inverse, the precision, it's actually precision, it's not precision the way that I say it. So precision, how precise you're being. So given mu and x times our prior distribution on sigma inverse. And if you wanted to, you could come up with a representation where we could all do this on the inverse scale, and that would be an inverse Wishart distribution that we play around with for the covariance matrix. You'll note that in the last homework assignment I gave you, the last problem, I have it on sigma scale. Everything that I've given you. If you'd like to know where I came up with that prior, that is the Jeffreys prior or the reference prior for sigma. And it's the conjugate limit of the inverse Wishart.
Are Jeffreys priors and reference priors the same?
In one dimension. So that doesn't really address the question here. So for one parameter, it's true. So, but jointly, no, they're not the same. So very often what we've done so far is we're usually taking the product of independent priors. So if you're operating like that and you like to use the product of independent priors, then those independent priors, the reference priors and the Jeffreys priors, are the same. It's not obvious that that's true, and it took people a long time to prove that. So for mu, the reference prior, let's just go back to the scalar analysis. For mu, the reference prior is flat. For phi, the reference prior is 1 over phi. If we came up with the Jeffreys prior, we'll talk about this maybe next week, the joint Jeffreys prior is not 1 times 1 over phi. But the reference analysis is usually based off of 1 times 1 over phi. And so if you didn't want to encode joint knowledge and have it jointly transform invariant, you could do something different. I almost never see that done. So just keep in mind, and I think it's probably a human limitation, that when we think about parameters, we think about them marginally. And so if you're going to base all of your inferences and insights off of the margins of something, after you've integrated out the parameters, so you're not doing an independent analysis, you're doing a marginal analysis, which takes into account their joint behavior. But if you're going to think about everything just marginally at the end of the day, and you're going to make your table where it's like, here's what I think mu is, and here's what I think phi is, then it's adequate to think about everything as the independent prior form. And that's what most people do. We'll clarify that next week if we have time. We're almost certainly going to get the Jeffreys priors next week. Okay, so good question. Okay, so let's just write all this down. So the likelihood function looks like what we just wrote down, sigma inverse to the n over 2, e to the minus 1/2 trace of the sum of the outer product. Wrong way. There's the likelihood function, and now all I need is just this part upstairs. So the normalizing constant's not going to come into play for us. We're not going to use it. But I will tell you, if you wrote down this for the inverse Wishart distribution, the integrating term that you're looking for would be analogous to that term right there. So when I ask you to integrate out the matrix, I'm not actually expecting you to do it. You're going to do the same thing that you've done the whole time. You're going to look up what the inverse Wishart distribution is, and you're going to look for that matrix right there, and your integral is going to integrate to the inverse of that thing. So same game that we did with the gamma distribution. I didn't mention, this is the k-dimensional gamma function. And what is it? It's like the integral of this stuff upstairs. So it's like that. Has something to do with these things too, but if I ended up taking omega to be the identity, so, and I picked gamma to, I guess I would still have this term in here, but if I picked omega to be the identity and I integrated over all of this stuff, it would integrate to that thing. So that's the definition for our purposes. I'm never going to ask you to play with that in this class. It's never come up to be something that was overly useful for me. So I won't spend too much time thinking about it. Okay, so we're going to have our Wishart distribution. So I will reparameterize all of this. So this is just going to be sigma inverse. So that's taking the place of V, and I'll have gamma minus P minus 1. So I think I changed everything to P dimensional for no good reason in here.
So K is the dimension.
K is the dimension of the problem. Yeah, sorry about that. So So this thing right here is a k by k. It means the p that we're using over here. I never understood why professors did this. So where they changed the notation unnecessarily in the middle of their thing, and now I understand why they do it. So they just lose track. So e to the minus 1/2, I'll put in my trace. I've got my omega inverse, and I've got my sigma inverse right in there. So, and that's everything for us. So we can combine our terms. This is going to be sigma inverse n over 2. We'll combine this with that. So this will be plus gamma minus p minus 1. So just like before, that minus 1 dangling off in the gamma distribution, I never touch that thing. I leave it there so I can recognize the important terms. So that's going to be one of the parameters defining this Wishart distribution. And this will look like e to the minus 1/2. Trace. I'm going to do this all at once. I could add together these two traces and then bring, using that same identity, trace of a plus b is equal to the trace of a plus the trace of b, but instead I'm going to do it all in one fell swoop and just combine all the terms. So this will look like sum of the xi's minus mu, xi minus mu, transpose. So a little bit of algebra, plus omega inverse right in here. That goes from I to 1 to n times sigma inverse. So just to be clear, what I've done is I combined the traces and the exponents, and then I absorbed the two terms together and I factorized appropriately so that I can write it all like this. Hopefully you can do that. And so, and I know at the end of the day what this is. So this is going to be a Wishart. It's going to have some parameters. N over 2 plus gamma. That's looking pretty good. The n shows up about where we think it will. And then we have this other term. Sum of the xi's minus mu times xi minus mu transpose. I goes from 1 to n plus omega inverse. And here's the part I always forget. Invert. That whole thing. So where did that invert come from? If you just remember, that was inverted, or that one wasn't inverted, right there. So just to follow the same notational pattern, this thing is inverted if that's the thing that's up here. Just to save you some worry on the midterm, I'm not going to ask you about Wishart distributions, so you don't need to memorize any of this. So we'll come back next time and we'll just show what the expectation of this thing is. Hopefully you can do it real quickly. It's that thing times that thing, and that has something very appealing for us. It's very similar to the classical estimator for variance, but on an inverse scale, because we put everything on an inverse scale. So we'll come back, we'll finish up with just a minor discussion. I'll write out what the entire likelihood is for the RAP problem and show you what the steps are that you need to complete the homework. If you're good at writing down joint distributions and understanding the likelihood and factorizing it appropriately, you've already done it. But we'll spend 10 minutes doing that, and then maybe it's a good time to jump into Jeffries. We'll do it slowly because I know you have a midterm on Wednesday, and then we'll come back to that on Friday. We'll have a review on Tuesday, so bring your questions there. We'll also do a yes, no, maybe session on Tuesday where you can ask me what's on the exam and I'll try and answer you. Let me also get your homework back as well. And if you have any questions on this homework or any of the homeworks, you can also ask before we start the yes, no, maybe sessions We can go through some details and then do yes, no, maybe. If there's going to be a lot of questions on Tuesday, then we might do yes, no, maybes for those that just want that part, and then we'll go through all the exhaustive details, and I'll stick around as long as I need to. Nicholas Keith.